Hi, class. So this is our last lecture in chapter 19, and we're going to be using worksheet 35 that you see here. This chapter will be on, or this lecture will be on chapter 19.3, and we're going to discuss the magnetism and color in coordination compounds. So I'll start my PowerPoint. There we go. So in chapter 19.3, we're going to start off by looking at why things are colored. So understand the origin of color in substances. And then we're going to look at what happens to the d orbitals in the transition metal ions when the ligands complex with the metal ion. And then lastly, we're going to look at a theory called the crystal field theory that explains how what happens to the d orbitals, and then from that we'll look at the colors and also magnetic properties of these complex ions. So first, let's see, light. So color is a manifestation of how our eyes interact with light. And so the kind of light that we saw, when we see color, our eyes only see visible light. Of course, light occurs over a wide range of frequencies. It's called, light's electromagnetic radiation. And this is a graph showing the wavelengths of light from the sun. So solar radiation. And that's what produces the colors in the objects we see around us and in nature. And so this basically shows all the wavelengths of light on the bottom. Let me move I don't know if this is in the way, but let me get this. So what the wavelengths go from short wavelength here, about 250 nanometers, up to long wavelengths of 2500 nanometers. And if you remember, if you studied light in physics, you know that wavelength is inversely related to energy. So short wavelength light is high energy light, and long wavelength light is low energy light. And so the solar radiation that we get here on Earth is filtered. It has to go through the atmosphere. And there's some UV light, which is from a wavelength of about less than 250 nanometers up to about maybe 450 nanometers. And then visible light occurs. We call visible light is the light that our eyes are sensitive to. So that's how we designate visible light. We can see objects that interact with visible light. And then beyond visible light, longer wavelengths is infrared light, which is commonly referred to as heat. And then as you go on, you get into longer wavelengths, and the longer wavelengths turn out to be radio waves and such, but those don't come from the sun. So this is just solar radiation. So this also shows the radiation that impacts the surface, the Earth, say at sea level. That's what's in red. So those are the wavelengths that get down to us at sea level as the solar radiation goes through the atmosphere. There are a few dips in this. Let's see, here's my cursor moving around. So these little dips in this red region is the radiation that is absorbed by water vapor in the atmosphere. And so the water vapor is preventing us from being exposed to some of the solar radiation. Actually, the upper atmosphere protects us a lot from a lot of UV radiation. It filters out quite a bit of visible radiation also. And then some of these other longer wavelengths are also filtered out by water. Oops. Let's see what happened here. Okay. So talking about visible light. So visible light, if you is made up of different wavelengths, and these different wavelengths, when we if we could separate the wavelengths, which happens when you see a rainbow, is that you get colors from purple to red, basically, and these represent the wavelengths that impact our eyes, and our brain interprets these as different colors. Okay, so that's why they're colors. You know, not every animal or species sees the same colors. So it depends on how the biochemicals in your eyes, the receptors, interpret those colors, your brain. And so, but we're all humans, we all pretty much see the same colors. So in this example, it shows white light, which is all these different colors. When you put them all together, it's white, impacting a sample of a blue substance. Well, that blue substance is blue because the white light, or that blue solution, is absorbing the red and orange wavelengths at the bottom. And so these wavelengths at the bottom are absorbed by the solution and don't go through the solution. So what our eyes see, the color we see, is the remaining wavelengths that come through. So that's a transparent solution. That's a solution where the light can go through. So that's what happens is when you see a color of a solution that's transparent, you know, light can penetrate it. What you're seeing is a light that is not absorbed. So what you don't see is the absorbed light. So there's a color wheel over here, and it roughly it kind of tells you what's going on. If you absorb light on this side, if this side is being absorbed, what you're going to see is something like this. So this is kind of a rough example. I mean, this color wheel is a rough approximation of what color you'll see. If the yellow light or the orange light over here is absorbed, what you're going to see is a blue light coming out the other side. And that's what this example shows. But in reality, it's a little more complicated than that, because solutions and chemicals, especially pure chemicals, absorb only certain wavelengths of light. All the rest of the wavelengths go through. So it's that mix of wavelengths that determine the color that you see. Now, this is for a transparent sample. What about something that's solid, the light doesn't go through? Well, in that case, what you're seeing is reflected light. So the light impacts the solid is going to absorb certain colors, and the colors that are reflected off are what your eyes see. But we're going to talk about solutions now, transparent solutions that light can go through. And because that's the complex, or the coordination compounds that we're talking about, they're all ions. When you put them in solution, they dissolve, and they make brilliantly colored solutions. But you can see through them. You know, they're transparent. Okay, so what's going on with these? Here's the d orbital. So I said we're going to come back. So let's look at these d orbitals. So we have 5 d orbitals. We know that that are important in these transition metal complexes, and they're labeled here. So we have it along the top. We have d 3dxy, 3dxz. Then the next row we have 3dyz, and then 3dx squared minus y squared, and 3dz squared. And these all have different shapes. What's important about these orbitals is how they're oriented. You'll notice that there's a 3-dimensional axis, an XYZ axis. And the orientation of these orbitals along these axes is what's important. And this is going to, later on, we'll talk about a model that we use to explain what's going on with these orbitals when ligands approach the orbitals. And remember, the ligands, the complex ions, when in the coordination sphere, it depends on the coordination number. Remember, if you have a coordination number of 2, the complex ion is a linear ion. So you can imagine that a linear ion might line up on the x-axis here. You know, coordination 2 is a linear substance, and so you might have, it might be the ligand might just be on the x-axis. Well, if that's true, it's going to really impact the dx squared minus y squared, because those orbitals are right on the x-axis, x and y-axis. So the ligands could be there for linear, or they could be along the y-axis for linear. So that dx squared y squared, an orbital there is going to be really impacted by the ligands. A tetrahedral, remember, is at the corners of a tetrahedron. Well, none of these orbitals are pointing at the corners of a tetrahedron, so they might not be impacted as much. If you remember the octahedron, there are some ligands that are on the corners. Remember, the octahedron looks like this. The ligands are on the corner of every axis. That's what an octahedron looks like. And so you can imagine that the x squared, y squared, and maybe the z squared would be really impacted, because those d orbitals are lined up along the x, y, and z axis. And indeed, that's what we're going to see later on. So here's a model of what goes on when the ligands approach a metal ion. So on the left side, we have 5 d orbitals, and they're degenerate. Remember, they're all the same energy. There's energy axis here on the left side of this. So as the ligands approach, they produce an electrostatic field around this ion, and that electrostatic field, because there's electrons in there, right? The positive ion has a lot of electrons, depending on whether it might not have any d electrons, because maybe that ion has a high charge and the d electrons are all gone, but it does have a lot of electrons. So when these ligands approach, which are full of electrons, remember the ligands have a lone pair of electrons, they create an electrostatic field around it. And the way this electrostatic field is like the electrostatic field in a salt. So in an ionic compound salt, like sodium chloride, where you have alternate positive and negative charges, you get a uniform electrostatic field around all the ions. And so that's what this model is. And that's why it's called the crystal field theory, because this electrostatic field that we're using to approximate formation of this complex ion is like the electrostatic field that you get in a crystal. Okay, so that's where that name comes from. So anyway, so initially this is what happens, but it doesn't stay this way. It turns out, like I said previously, the ligands are approaching, we can think of the ligands as approaching this metal ion along the axis, and some of these orbitals are lined up along the axis. So this particular model has to do with an octahedral complex ion. Remember, octahedral complex ion has 6 ligands, or 6 as a coordination number of 6. So that's what's shown here. This shows, let me move this around. So this shows our central atom, and it shows our ligands, these negative charges, these point charges on the outside. So if it's a chloride ion, it'd definitely be negative charge. If it's a water molecule, it doesn't have a negative charge, but it has a pretty good electron density around the oxygen. So anyway, so you can see these point charges at the X, Y, and Z axis. So this could be the X axis here. This could be the Y axis over here. And this is the Z axis up here. And so what happens, well, in the previous slide, I said the dz squared and the xy squared are lie right along those axes. So their energy, the energy of those gets bumped up. So this interaction with the ligands really increases the energy of those two d orbitals. So you get this increase in energy of those d orbitals. And on the other hand, the other d orbitals don't lie along the axis, so you get a decrease. So they, from this electrostatic crystal field, this uniform field, the energy of the other d orbitals goes down. So they go below the field, and the energy of the dx squared minus y squared and dz squared go up. And the difference in energy is called the crystal field splitting energy, this delta. This delta is and the O stands for the octahedral case. So an octahedral ligand, you get a crystal field splitting that looks like this. And it always is like this. So the dxy, dxz, dyz are three lower energy orbitals. And there's symmetry. There's a symmetry designation called the T2G. So those three orbitals called the T2G orbitals. And then the EG orbitals, the dx squared minus y squared and the dz squared orbitals. And they're higher, way higher in energy. So the splitting turns out for an octahedral complex, because these ligands come right in, that the splitting varies a lot depending on the ligand, and it varies a lot depending on the metal ion. The higher the charge on the metal ion, the greater the electrostatic interaction, the closer the ions come, because there's a greater pull for the negative charge. But the closer they come, the greater they interact with the electron, the greater this crystal field occurs, and the greater separation in these. And so it's not a constant splitting. It's different for every ion ligand combination. We know there's a lot of those. So we're just going to look at some simple cases just to try to understand what's going on with the color magnetism that goes on. So when everything settles down, let's see, let's move this over here. Finally, you get this splitting. So this was a high energy splitting, but when the ligands get close enough and form the chemical bonds, so you gain some energy. So when it forms the covalent, finally, when the ligand gets close enough to the metal ion, it forms the bond where the ligand donates a pair of electrons to the metal, forms this coordinate covalent bond, which is a really strong bond, almost like a covalent bond. And the energies of the orbitals go down. So you can see the energy of the orbitals now are split across the up and down over where the original energy of the d orbital. So the EG orbitals increase in energy a bit above where the degenerate d orbital energy was originally, and then the T2G orbitals decrease below that. So they're really very stable. Okay, so now we're going to look at what's going on, say, with an iron to metal. So here's a specific example. So iron 2, so iron has, if you look at the fourth period, it has this 4,2s and 3d6. And you can look at your periodic table to figure that out. So if we go look at the periodic table, you go across 1, 2, 3, 4, 5, 6 of the elements in the D shell. So we know there's 6 Ds. So the Fe2 plus is lost to 2 s electrons, so there's 6 Ds left. So we know that iron, and I'm going to write it right here, it's a D6. It's a D6. Whoops. Come on. A D6 ion. So how do they fill? Let me go first. So the D6 and the degenerate d orbitals would look like this. So they fill singly, 1, 2, 3, 4, 5, and then it would pair up in the first d orbital. So that's what a D6. But when the ligands come and you get the splitting, the crystal field splitting, it might look like this. So this is kind of a narrow crystal field splitting. And in this would be called a weak field. So the weak field means it's just weakly split. There's not a huge difference in energies between the T2G and the EG. And so the delta is small, I would say. I could write that maybe. See, the delta sub O is, we'll just say it's small. So that's what happens with the octaves. Remember I said the splitting isn't constant, it's not the same. So when you get a small splitting, it's called a weak field split, a weak field. And when you add the electrons to a weak field, they add just like they do to the degenerate D orbitals. So it goes 1, 1, 1, 1, 1, and then they pair up in the lower energy orbital. But there's another case, and there's kind of a continuum, but we're just going to look at a simple case. There's another case where you get wide splitting, and that's called strong field. So this is weak field. We call this a weak field split. And this one would be called a strong field split. And in that case, the delta oct for the strong field is bigger. So the delta O, so maybe we could designate it. We could call this one the delta O weak, and this is the delta O strong, and the delta O strong is greater than the delta O weak. So what happens? Because the T2Gs are or the gap between the two TGs and EG is great, you're going to pair up in the T2G before you add electrons to the EG. So you go 1, 1, 1, and then pair, pair, pair. And then if you add extra electrons, you start putting them in the EG orbitals. And what it is, there's another energy going on, and that's called pairing energy. So there's an energy cost to pair up the electrons because, of course, they both have negative charges and they repel each other. And so if the pairing energy is greater than the delta, then you're gonna go into each individual orbital before you pair. So in the weak field case, the delta OW is less than the pairing energy. Because to pair up, so you're not going to put 1, 2, 3 and then pair up because that's the greater energy cost than putting it in the higher orbital in the weak field case. In the strong field case, though, delta OS and delta OS, delta O strong field is weaker. Let's see, now delta OS, no, sorry, that's wrong. I wonder if I can undo that. I don't know if I can undo that. I'll just cross it off. Delta OS is greater than the pairing energy. So what's going to happen is you're going to put 1, 1, 1, and then you'll pair them up before you start adding electrons up here. Okay, now we only have 6 electrons, so we put 6 electrons in the lower energy level orbitals first. Now let me kind of didn't clean up. Okay, so let's look at these now. Now the other thing is you can see there's labels on here that says in the weak field case it's called high spin, and that has to do with how many unpaired electrons there are. So you can see in the weak field case, we have lots of unpaired electrons because the electrons went into the orbitals individually before they paired up. And that's called the high spin case. Remember, each electron, if you go back to talking about electron configurations and some characteristics of electrons, is that they have positive spin and negative spin. And when they're paired up, the positive spin cancels the negative spin. So the electrons in that orbital, if they're paired, have no spin. Spins cancel. But if the electrons are individual in an orbital, then there is spin. So in the case of the weak field case, we have 4 individual electrons, so that's called the high spin case. In the strong field case, where we filled up the lower energy orbitals first, they're all paired up, so there's no spin. So that would be called a low spin case. So a low spin case occurs when your crystal field energy is much greater than the pairing energy. So it'd be a large delta is the case where you get the low spin. So that's always the case. So it doesn't, if there were some unpaired electrons in the strong field split, it would still be low spin. There'd still be less spin. Say we had 5 electrons instead of 6, or you'd have 5 individual electrons in the weak field case, and you'd have one lone electron in the strong field case. So it'd still be a low spin. It'd still have less spin than the other case. So strong fields are always low spin, and weak fields are always high spin. And I think that's what it says at the bottom of this slide. We've got all these things. I don't know if that's coming. I've got all this stuff on my slide that I can't, that are blocking parts of the slide. But there's some comments here. Number 1, in the absence of a crystal field, the orbitals all are degenerate. Then with weak field ligands such as water, the ligand field splitting is less than the pairing energy. So the electrons occupy all the orbitals singly. Or coordination complexes with strong field ligands, such as using cyanide ligand, the delta O is greater than P, and the electrons pair in the lower energy T2G orbitals first before occupying the higher energy. What about spectral properties? Okay, so I talked about the magnetic, I didn't talk about the magnetic properties. So there are 2 kinds of magnetic properties, and those are called paramagnetic and diamagnetic. Kind of messed up my slide here, but paramagnetic, you can go right at the bottom. I'll write these words, paramagnetic, oops. Let me go back up. Paramagnetic. Paramagnetic and diamagnetic. Paramagnetic are complexes that actually are magnetic. Diamagnetic are complexes that are not magnetic. So ions where all of the d electrons are paired up, if there are no single unpaired electron, if there's 0 unpaired electrons, like this FeCN6, like in this strong field case on the right, they're diamagnetic. So diamagnetic requires all electrons to be paired up or no electrons. Okay, so but if there's even one unpaired electron, the complex ion is going to be paramagnetic. I'll say that again. Paramagnetic means that there's at least one unpaired electron. Diamagnetic means that all the electrons are paired. So in this case, the weak field case is paramagnetic and the strong field case is diamagnetic. And we know that the energy, so what happens when light is absorbed? So we looked at that schematic where light's absorbed in the blue solution, and it's blue because only blue light is transmitted and the red and yellow is absorbed. Well, the red and yellow light, if you remember, was kind of a low energy light. And so low energy has to do, the energy of the light that's absorbed has to do with the split here, with the delta. So if the delta is low energy, that means low energy lights can be absorbed, because what happens is an electron goes from a lower energy orbital into an upper energy orbital with the absorption of light. So when that delta is equal to the wavelength of, or equal to the energy of the light, the electron will be promoted. One electron will absorb that light and go up to a higher energy orbital. and then and then it comes back down, and it comes back down by different ways. It releases energy, but energy can come out of it in different ways. And then it'll go back up and absorb more light. There's also, there's lots of, 1 mole is 6 times 10 to the 23rd. So there's lots of ions in there that can do this. And so the light that goes through is the light that's not absorbed. So the weak field is going to absorb low energy light. The strong field, because the gap is greater, that's higher energy, is going to absorb higher energy light, which is shorter wavelength. So the weak field absorbs long wavelength light, and the strong field absorbs short wavelength light. So we'll see examples of that later on. So here's this slide is going to show what happens to the octahedral splitting crystal field, splitting d electrons in octahedral complexes with different types of ions. So we're going to start with the D1. So there's 1 d electron, and this is would be an example, would be titanium 3+. I guess what we didn't show here is scandium. So there is one more ion. There's scandium 3+. I give it over here. Scandium 3+. Remember, that's the scandium ion. That has 0 d electrons. So that's a D0. So D0. So D0 isn't on here, but D0 wouldn't have any electrons, right? So it doesn't matter if the field is weak or strong. There's no electrons. All the orbitals are empty. So that'd be paramagnetic. And it's not going to absorb any light because there has to be an electron that goes up to a higher energy orbital. So if there's no electrons, there are no electrons to be promoted to a higher energy orbital. So a complex ion like scandium with 0 electrons is clear. Doesn't have any color. And I have a slide that shows that. Okay, the D2 case looks like that. And it turns out, and let's look at D3. So that looks like that. So this is the same for strong and weak fields. And I think I have that at the end. So I'll just go through these. We'll look at all of them. There's D3. So strong and weak fields are the same for these. And you can picture that. It doesn't matter how separated the orbitals are, that's how they're going to fill. All the lower energy ones up to D3 will fill. Okay, but when we get to D4 is when they change. So the low spin case or the weak field case, low spin, remember, is weak field. So I'll put weak in here. And this, sorry, I did the wrong way. This is weak up here. Man, I'm really having trouble there. This is strong here. Okay, so that's strong. So the weak field case, they go individually. The strong field case, they pair up, remember, in the lower energy orbitals first before they get promoted. So high spin, so the strong field is called low spin, and the weak field is called high spin. And they're going to be different now as we go through. So to D5, D6, and D7, there's a difference between the occupation of the orbitals by electrons. There's a difference between the strong and the weak field cases. And lastly, when you get to D8, D9, D10, they're all the same. So it doesn't matter if you have a weak or strong field, it's the same. Now, if you have an empty orbital, like if there's not an empty but a partially empty orbital, so in the D8, there's room for an electron, so you can still get absorption of light. When we talk about the spectral properties, an electron can still be promoted from a lower energy orbital to a higher energy orbital. And however, in the case when you get to D10, there's no space for the a lower energy electron to go to a higher energy orbital because the higher energy orbitals are full. So we'll see an example of that. So like I said before, in the D0 case and the D10 case, we would predict that the solutions would be colorless, that all light, there's no light absorbed, all white light is transmitted. So that means, the solutions are just clear. Okay, so we just got through looking at the octahedral splitting. Here's a couple of other splitting. So this is in the tetrahedral crystal field is shown on the left side. And remember, a tetrahedron looks like this. So here's our tetrahedron. We can go like this, and we can put a wedge here. We put a dashed line here, and our ligands are out on the corners here. So in the tetrahedron case, the ligands are not lying along any axis. And so the splitting isn't very great. So what happens, the way the electrons fill in a tetrahedral crystal field is they fill just like the degenerate. They fill in a like a high spin mode. So they'd fill individual orbitals individually, or they fill singly into each orbital until they have to pair up. So you'll also notice that the z squared and x squared y squared are flipped. So they're lower energy now, and the dxy, dyz, and dyz are higher energy. Okay, the other most common is a square planar. So I'm just looking at the common ones, but remember there's linear structures, trigonal planar structures, tetrahedral, square planar. There's pyramidal, which is a 5, coordination number 5. There's octahedral, it's coordination number 6, and then there's coordination number 7 and 8, and even higher. So the structures kind of get more and more complicated. Each structure has its own crystal field splitting. We're just looking at 3 of them here. So octahedral is most common, and this is just an introduction. And then the coordination number 4 is the second most common. And so that's what we're looking at for coordination number 4, there are 2 shapes, the tetrahedral and the square planar. And we can say the square planar maybe is just like this. And you can imagine in the case of square planar, the ligands are lying right along the x and the y axis. And so the dx squared minus y squared is really impacted. Okay, that's the orbital that lies along the x and the y axis. So its energy goes way up. It's really high. It's almost in isolation up there. The other orbitals are much lower. So the other orbitals kind of feel singly. The energies are pretty close together. The dz squared is about even with, well, here's a line that shows the kind of the neutral point, if you will, of the, I guess in the electrostatic model, crystal field model, this is where all the Ds would be, and then they go up and down from there. And so the DZ really, it looks like it's a little higher energy, but it's not really much higher than it normally would be. Dx squared minus y squared is way up there. And so when you add electrons to this square planar model, you would fill all the lower ones first, probably just singly. The dx squared and y squared are filled really last. Okay, so only if you got up to d9, d10 would there be any electrons in the dx squared minus y squared. The energy is so high. In fact, that's higher than in a octahedral complex. Remember the splitting octahedral, the x squared minus y squared and z squared up there. This in the square planar model, the dx squared minus y squared is really high. Okay, so what's going on? I said we review this. So here's a case. This is a D9 ion, and I don't know if this is, you can't tell if it's a weak field or a strong field because it's a D9, remember? And the filling was the same. So in this case, this shows that an electron is being promoted from lower energy to higher energy with absorption of this orange light. And so what happens then is that here's orange on this side. So this is being absorbed and then this is being transmitted. So the solution is blue. Well, that looks pretty good. So we can use the color wheel for that. What's really happening, if you look at the absorption spectrum, which I think you did, I think in lab you've looked at some absorption spectrums, you might see something like this, that the light at 498 is being absorbed. And so that means this is being absorbed at 498. That means all this light on the other side of it, over here and over here, is being transmitted. So it's the combination of those colors that give the solution its color. You know, you combine them all, and that's what it looks like. So on the left side is showing a solution of copper 1 chloride, which is a D10 complex ion. So it has 10, copper 1 has 10 D electrons. And you can see if you have 10 D electrons, the solution is colorless because all the orbitals are full. So there's nowhere for an electron to go. On the other hand, scandium would also be, scandium 3 plus would also be colorless. And on the right side, you have D9, copper chloride. So that has 9. There's one lone pair, or there's one space. Remember the D9 case was shown here on the left. This is D9. So there's a space there, so you can promote electron. And that's blue. In fact, maybe that's what this solution represents here, this schematic, and maybe that's copper 1 chloride there in that solution. And here's an example of different ions. So these are different ions with partially filled D shells, except for on the very ends. So this end and this end. So on the first position is a D0. So those are clear. And the last position is a D10, and that's also clear. And in between, you have different complex ions with different numbers of the electrons. So I have a legend down here. I'll just write over the top. So this is D3. This is, let's see, D3, D7, D8, and D9. D3, D7, D8, and D9. And so you can see they all give different colors, and the colors are very, very brilliant. You know, they're cool. They're neat colors. So these compounds give really an interesting color. So that's the end. I'm going to go over to the PowerPoint and not the PowerPoint, excuse me, the worksheet. And the worksheet will be a review of or summarize some of this stuff. We'll go over some of these things we just talked about in the lecture. So I'll stop the share. And here's the worksheet. So the first page of this worksheet 35 is really a summary of what I just went over in lecture. And so I'm not going to go over it again, but it does have at the bottom, it has a schematic or diagram of the octahedral, tetrahedral, and square planar splitting. And there's some notes here on the left side. It says some points to consider when you're looking at crystal field theory. And you might read that over. It's a summary of what we just talked about, that the position of the ligands are important, that the structure, of course. So it depends on whether you're talking about a linear structure, a trigonal planar structure, or whatever. So that's going to depend on how the ligand then interacts with the d orbitals. The most common structures, there's a couple notes here. The most common structures for square planar are D8 metal ions. And I think that makes the most stable electron configuration in the d orbitals. So the square planar, remember, looks like this. So if you have eight electrons, you go 1, 2, 3, 4, 5, 6, 7, 8. So you fill all these lower d orbitals. So when they're all paired up, you get extra energy. So you gain some energy. So that's a real stable electron configuration. And that happens. So the kinds of complexes, remember we talked about coordination numbers 2, 3, 4, 5, 6. Well, those those are going to form the most stable complex ion is going to form, and that's going to depend on the ligand and also the number of electrons that the metal ion has. So that's why some metal ions form square planars, some form octahedral complexes, some form tetrahedral complexes. So I'm not going to go over that. I'm going to go straight to the worksheet and we'll work a couple of problems. So what I'd like to do is I'm going to work just problem 1. And then I want you guys to do problem 2, which is an extension. It's like 1. So I'll go over 1. That'll kind of show you what I want you to do. And then I want you to do problem 2. And then on the next page, problem 3. So I want you to do 2 and 3. And no, it doesn't say 3. This is supposed to be 3. Okay, that's supposed to be a 3 over there. So problem 3 talks about the spectral properties. So the light properties, of a complex ion here. So it's just answering a few questions on these complex ions. So I want you, we just talked about that, what's going on with the light and why these different complex ions have different colors. So that's what those questions are about. So I want you to answer those. The first page has to do with filling the orbitals and also asking about their paramagnetic and diamagnetic properties. So problem set 1, it says, draw the splitting of the 5d orbitals in a tetrahedral complex into box A and box B. So a tetrahedral complex. So you can do lines or boxes, but I would, I kind of like boxes. So I'm going to go like that. And if you need to refer to what the splitting looks like, you can always look on the front page because I've got the splitting patterns there. So it just says to draw these here. So I'm going to draw them. So that's the first task, be able to draw those. And you might also think about labeling these. Remember where there's 3? It's the, I think the 3 was, let me look, see what I got here. Oh, geez, sorry about that. Okay. I don't know, I think the 3 were the, maybe I have a better memory than I have to go look again. One's an E and one's a T, remember that. So in the octahedral, the orbitals were labeled T2G and E2G. In the tetrahedral case, which is kind of the flip of that, they're labeled E and T, but the 2G is off. So in box A, add electrons for a D5 complex. So this is going to be a D5. Maybe we'll put D5 there. So just as a reminder. And in box B, right, add electrons for a D10 complex. So I'll put a D10 there. So in the case of the tetrahedral splitting, remember, they're all really close together, so they fill singly. So for the D5, it's 1, 2, 3, 4, 5. It's like that. And for the D10, it would be just, they'd all be paired up. I should actually go fill them singly first, because that's what would happen. And then you pair them up. I'm going to pair them up. Okay, so that's tasks 1 and 2. The third one of these diagrams represents a paramagnetic ion and the other a diamagnetic ion. Fill in the blank with either box A or box B. So in box A, we have a bunch of unpaired electrons. So unpaired is diamagnetic. So this is box A. And box B would be diamagnetic. So that's it. So I think I said it early on, in this chapter, there are no calculations. There's all these conceptual items, conceptual knowledge that I want you to know about complex ions and coordination compounds. So this is the kind of task that we'll ask you, the kinds of questions we'll ask you to do. So I'd like you to do questions 2 and questions 3 on the other side. And this is one of the worksheets I want you to turn in on this chapter. So good luck if you have any questions. I have office hours on Monday. The worksheets, the homework aren't due until Wednesday of next week. I think I put it up, I think it's August 4th. I have a calendar here. Or August 5th. So the work on chapter 19 is due August 5th. And that's it for now. So this is quite different from what we've done previously, but it's pretty interesting stuff. So take care, and I'll see you next time. Next chapter is organic chemistry. Goodbye for now.